This presentation examines how urbanization affects biodiversity and how ecological connectivity can reduce habitat fragmentation in cities. It introduces the impacts of urban expansion and infrastructure barriers on ecological resilience. Key principles of urban ecological networks are presented, including core habitats, corridors, stepping stones, and vertical and horizontal green connections designed to meet species-specific needs. Practical design solutions such as green infrastructure, wildlife crossings, ecological zoning, and nature-inclusive architecture are discussed. 2 case studies, the Vancouver Greenest City Action Plan and Basel's Green Roof Network, illustrate how these principles can be applied in real urban contexts. The presentation concludes with reflections on integrating ecological connectivity into urban planning and design. Understand the concept of habitat fragmentation and connectivity in urban settings. Learn design strategies that support habitat continuity and wildlife movement. Explore tools and topologies that integrate ecological networks into urban form. Urbanization and habitat loss include following aspects. Urban growth disrupts natural habitats and migration routes. Fragmentation reduces biodiversity and ecological resilience. Connectivity restores movement, breeding, and ecosystem function. Urban expansion and its ecological footprint. Rapid urban growth converts forests, wetlands, and grasslands into built environments. This transformation replaces complex habitats with impervious surfaces, reducing food sources and shelter for countless species. Beyond simple land cover change, urbanization alters temperature, hydrology, and light regimes, creating urban heat islands and pollution gradients that further degrade ecological conditions and push wildlife toward marginal areas. Habitat loss, the primary driver of biodiversity decline. Urban development is one of the fastest-growing causes of habitat loss worldwide. Each new road or housing zone fragments what were once continuous natural systems, reducing viable territory for species that depend on large or undisturbed areas. As vegetation disappears, local extinction risks rise, especially for specialists and ground nesting or migratory species. The loss is not only spatial but also functional. Nutrient cycles, pollination, and carbon storage all diminish. Disrupted migration routes. Many species rely on seasonal migration or daily movement between habitats. Urban infrastructure, highways, buildings, and fences, creates physical barriers that block these routes. When migration is interrupted, populations lose access to feeding or breeding grounds, leading to genetic isolation and demographic decline. For birds, bats, and large mammals, even light and noise pollution can distort navigation cues and timing. Fragmentation and edge effects. Fragmentation divides ecosystems into smaller, isolated patches. The new edges expose core habitats to wind, predators, invasive species, and human disturbance. Smaller fragments support fewer individuals and species, disrupting ecological networks. Over time, isolation lowers reproductive success and resilience to stressors like drought or disease. Declining biodiversity and resilience. Reduced species richness weakens ecological redundancy, the idea that multiple species can perform similar ecosystem functions. When diversity declines, systems become more vulnerable to shocks such as climate extremes or pest outbreaks. Urbanized landscapes thus tend to lose both stability and adaptive capacity. The result is not only fewer species but also diminished ecosystem services vital for human well-being, from water purification to temperature regulation. The importance of landscape connectivity. Connectivity refers to the degree to which organisms can move across a landscape. Functional connections, through corridors, stepping stones, or permeable land uses, allow migration, gene flow, and recolonization after disturbance. Restoring connectivity can counteract fragmentation effects. It enables populations to access resources, maintain genetic diversity, and adapt to shifting climatic conditions. Green corridors and urban design. Urban planners increasingly integrate green corridors, riparian buffers, and park networks that link isolated patches. These elements serve as safe pathways for wildlife and as recreational spaces for people. Designing cities with connected green infrastructure, street trees, green roofs, or bioswales, helps harmonize urban growth with ecological function, turning cities into parts of larger living systems rather than barriers. Monitoring and policy integration. Effective restoration requires monitoring habitat quality and species movement via remote sensing, camera traps, and citizen science. Data-driven assessments guide adaptive management. Embedding connectivity goals into national land use plans, transport design, and climate policies ensures long-term effectiveness and prevents future fragmentation. Toward resilient urban ecological futures. Balancing urban growth with ecological integrity demands integrative planning, aligning housing, transport, and conservation at regional scales. By preserving habitats, mitigating fragmentation, and restoring connectivity, cities can evolve into resilient landscapes that sustain both human and non-human life, ensuring ecological processes continue amid global urban expansion. Ecological connectivity is a central concept in landscape and urban ecology, aiming to maintain functional links between habitats within fragmented urban environments. Core habitats are relatively large, high-quality areas such as parks, forests, or wetlands that can sustain viable populations of species over time. Corridors connect these core habitats and enable the movement of organisms across otherwise inhospitable urban matrices. They can take the form of riverbanks, tree-lined streets, rail-side vegetation, or linear parks. Corridors facilitate dispersal, seasonal migration, and genetic exchange, reducing the negative effects of isolation such as inbreeding and local extinctions. Stepping stones are smaller habitat patches that function as intermediate resting or feeding points between larger habitats. Examples include pocket parks, community gardens, or vegetated traffic islands. Together, core habitats, corridors, and stepping stones form integrated ecological networks that enhance biodiversity, resilience to climate change, and the long-term sustainability of urban ecosystems. Urban ecological connectivity operates across multiple spatial dimensions, particularly through horizontal and vertical linkages. Horizontal linkages are landscape elements that connect habitats across the ground plane of the city. These include greenways, river edges, canals, street trees, and linear parks that allow species movement along continuous or semi-continuous routes. Vertical linkages extend ecological functions upward and downward within the built environment. Green roofs, living walls, vegetated balconies, and ecological bridges introduce habitat opportunities above ground level. These elements are increasingly important in dense urban areas where horizontal space is limited. Vertical connectivity supports insects, birds, and plants while contributing to ecosystem services such as thermal regulation, stormwater retention, and air purification. When combined, vertical and horizontal linkages create three-dimensional ecological networks that enhance urban biodiversity. Effective ecological connectivity planning must consider the specific ecological requirements of different species. Species vary widely in their sensitivity to habitat structure, disturbance, and environmental conditions. Corridor width is a critical factor. Larger mammals typically require wide, continuous corridors with sufficient interior habitat, while smaller species may function within narrower pathways. Vegetation cover influences shelter, foraging opportunities, and predator avoidance. Dense and structurally diverse vegetation benefits forest-dependent species, whereas open or mixed habitats may be suitable for generalists. Urban stressors such as noise, artificial lighting, and human activity can significantly reduce corridor functionality. For example, nocturnal species are highly sensitive to light pollution, which can disrupt movement and behavior. Designing species-sensitive corridors involves minimizing noise, reducing artificial lighting, using native plant species, and ensuring appropriate substrate and microhabitat conditions. Transportation infrastructure such as roads and railways represents one of the most significant barriers to wildlife movement in urban and peri-urban areas. Wildlife overpasses and underpasses are engineered structures designed to reconnect habitats separated by such barriers. Overpasses are typically vegetated bridges that mimic natural habitat conditions, while underpasses include tunnels, culverts, and modified drainage structures. Factors such as width, height, vegetation cover, and substrate must align with the behavioral preferences of target species. Well-designed crossings reduce wildlife vehicle collisions, enhance genetic exchange, and support population viability. In urban settings, wildlife crossings must often balance ecological effectiveness with spatial constraints, safety standards, and aesthetic considerations. Integrating these structures into broader green infrastructure networks increases their functionality and public acceptance. As cities expand, wildlife overpasses and underpasses are essential tools for maintaining ecological continuity and mitigating the fragmentation effects of urban mobility systems. Green infrastructure refers to strategically planned networks of natural and semi-natural areas that deliver a wide range of ecosystem services while supporting biodiversity. In urban environments, this includes parks, green streets, canals, urban forests, and restored waterways. Unlike isolated green spaces, green infrastructure is designed as an interconnected system that enhances ecological connectivity and multifunctionality. Parks serve as core habitats and social spaces, while green streets integrate vegetation into transportation corridors, improving connectivity and microclimate regulation. Canals and river systems function as ecological corridors that support both terrestrial and aquatic species. Together, these elements reduce urban heat island effects, manage stormwater, improve air quality, and enhance human well-being. Effective green infrastructure planning requires cross-sector collaboration and long-term governance frameworks. By embedding ecological connectivity into everyday urban spaces, green infrastructure supports resilient cities capable of adapting to climate change while maintaining high environmental quality and livability. Ecological zoning is a planning approach that allocates land uses based on ecological value, sensitivity, and function. It identifies areas for conservation, restoration, and sustainable development, ensuring that ecological networks are protected within urban growth processes. Zoning regulations can limit development in high-value habitats while encouraging green connections between them. Nature-inclusive architecture complements ecological zoning by integrating biodiversity supporting features directly into buildings. Examples include green roofs, nesting structures, permeable surfaces, and vegetated facades. These design strategies transform buildings from barriers into functional components of ecological networks. Together, ecological zoning and nature-inclusive architecture promote a holistic integration of nature into urban form. Institutional support, design guidelines, and interdisciplinary collaboration are essential to mainstream these approaches and ensure long-term ecological continuity in urban environments. The Greenest City 2020 Action Plan implemented by the City of Vancouver represents a concrete urban strategy for maintaining habitat continuity within a dense metropolitan context. A core objective of the plan is improving access to nature while strengthening ecological connectivity across the city. Vancouver expanded and linked parks, coastal habitats, and urban forests through green streets, restored shorelines, and urban biodiversity corridors. Projects such as the False Creek Shoreline Restoration and the citywide Greenway Network connect terrestrial and aquatic habitats while accommodating high recreational use. Native vegetation planting, daylighting of streams, and protection of wetlands support birds, amphibians, and pollinators. Importantly, habitat continuity is embedded in land use policy, infrastructure design, and building regulations rather than treated as isolated conservation measures. This case demonstrates how a municipal-scale planning framework can integrate ecological connectivity into everyday urban design. By combining habitat protection with climate adaptation and public access goals, Vancouver illustrates how biodiversity conservation and livability can be jointly achieved in a growing city. Basel, Switzerland, provides a well-documented example of habitat continuity achieved through nature-inclusive architecture. The city mandates green roofs on new and renovated flat roof buildings, resulting in an extensive and connected rooftop habitat network. These roofs are designed using diverse substrates and native plant species to support insects, birds, and rare invertebrates. Research referenced in green infrastructure and urban ecology literature shows that Basel's green roofs function as stepping stones between parks, river corridors, and urban gardens. This vertical habitat network compensates for limited ground-level green space and enhances ecological permeability across the city. Roof designs are tailored to biodiversity objectives rather than purely aesthetic or energy goals. Basel's approach demonstrates that habitat continuity can be achieved through regulatory instruments and building-scale interventions. By systematically integrating biodiversity into architecture, the city transforms its built environment into an active component of its ecological network. Urban design can support both people and wildlife. Habitat continuity enhances biodiversity and ecosystem services. Long-term success depends on governance, monitoring, and design quality. The expanding footprint, where nature gives way. The most direct and immediate impact of urbanization is the conversion of natural and agricultural land into built environments. This process, known as land use change, is a primary driver of habitat loss worldwide, replacing forests, wetlands, grasslands, and farmland with the impermeable surfaces of roads, buildings, and infrastructure. This expansion is relentless. This trend not only raises concerns for food security but also represents a twofold ecological loss, as urbanization can lead to the displacement of natural habitats to compensate for lost cropland. It eliminates not just the farms themselves, but also the semi-natural ecosystems like hedgerows and fallow fields that often exist within agricultural landscapes. Life on the edge, the problem of fragmentation. Beyond outright habitat destruction, urbanization causes habitat fragmentation, the process where urban development divides large, continuous habitats into smaller, disconnected patches. A contiguous forest becomes a series of green islands in a sea of concrete, and a sprawling wetland is sliced apart by roads and suburbs. This breakup has lasting and profound impacts on Earth's ecosystems, leading to both immediate and time-delayed biodiversity loss. The negative effects of fragmentation can be understood through three key processes. Isolation. Fragmentation creates physical barriers like roads and buildings that obstruct the movement of organisms. This disrupts essential behaviors like migration, foraging for food, and finding mates. For a ground-dwelling amphibian, a multi-lane highway becomes an impassable desert, effectively trapping it on a small island of habitat. Over time, populations become genetically isolated, reducing their ability to adapt to change. Reduced resilience. Smaller habitat patches can only support smaller populations of species. These smaller populations are inherently more vulnerable. A single disease outbreak, a harsh weather event, or a localized disturbance can wipe them out entirely, leading to local extinction. Edge effects. The boundaries, or edges, of these habitat fragments are exposed to a host of disturbances from the surrounding urban environment. These edges experience increased pollution, chemical, light, and noise, a higher likelihood of invasion by non-native species, and altered microclimates, e.g., higher temperatures and different light levels, all of which degrade the quality of the remaining habitat. The winners and losers. A new urban ecology. Urbanization acts as a powerful ecological filter, favoring species with certain traits while selecting against others. The general trend is a decline in specialist and sensitive native species, which are often dependent on specific, undisturbed habitats. In their place, generalist, mobile, and human-tolerant species, including many introduced species, begin to thrive. This process leads to biotic homogenization, where the unique flora and fauna of different regions are replaced by a similar-looking set of cosmopolitan, urban-adapted species, making cities worldwide ecologically more alike. The invisible transformation. Indirect urban impacts. The ecological influence of a city extends far beyond its physical footprint. These indirect impacts are environmental transformations that degrade the quality of remaining and adjacent natural habitats, often in subtle but powerful ways. The urban heat island effect. Urban materials like asphalt and concrete absorb and retain more solar radiation than natural landscapes. This causes cities to become significantly warmer than their rural surroundings, a phenomenon known as the urban heat island effect. This localized climate change can disrupt the natural world by altering plant flowering times, creating mismatches with pollinators and pushing species beyond their thermal tolerance. Altered earth and water. The proliferation of impermeable surfaces in cities changes how water moves through the landscape. Rainwater that would normally soak into the ground now runs off quickly, increasing flood risks and reducing groundwater recharge. Urban soils are often compacted by construction and foot traffic, which negatively affects soil organisms such as annelids and springtails that are sensitive to soil compaction and pollution. These altered conditions also harm plants and the mycorrhizal fungi essential for nutrient absorption. Pervasive pollution. Cities generate constant pollution that spreads into surrounding natural areas. Artificial light at night, persistent noise from traffic and industry, and chemical pollutants from vehicles and industrial processes can significantly affect wildlife by disrupting behavior, communication and navigation, and posing direct threats to their health. Designing cities for nature. The ecological damage caused by urbanization is not inevitable. The form of development strongly influences environmental impact. Planners face a choice between different growth models. Compact development emphasizes high-density growth within or near existing urban boundaries. While more efficient and reducing direct habitat loss, concentrated activity can intensify indirect impacts such as pollution and heat. Decentralized development, sprawl, involves low-density, spatially scattered growth that consumes far more land and is a major driver of habitat fragmentation and direct habitat loss. Sustainable urban planning provides opportunities to mitigate these impacts and redesign cities as ecosystems where both people and nature can thrive. Integrating ecological knowledge into urban design can create more resilient and biodiverse landscapes. Key strategies include integrating green infrastructure networks, protecting key biodiversity areas, and promoting nature-based solutions such as wetland restoration for stormwater management and vegetation to reduce urban heat.